about some of these complex issues around how we know what we're analyzing in data sets from these new instruments.
Great. Well, hi everyone. I'm Dave Tabb from over at Stellenbosch. I am really glad to talk to you about the problems of identifying spectra that we collect on these brand new TripleTOF instruments. Now, the TripleTOF is exciting. I mean, just to think about, even if it had exactly the same capabilities of the Q-Exactive and we could just run twice as many samples every day, we would already be pretty excited about that. But in fact, it does offer some new kinds of challenges with it. Now, I'm going to ask you kind of just a what-if question. If you were given a tandem mass spectrum that had the fragments of 25 different peptides in it, how would you determine the identity of those 25 peptides? You can just pause and think about that.
With considerable difficulty.
Considerable difficulty. All right. So we've mentioned the problems of convolution, that we have multiple fragments from multiple peptides all coexisting in the same space. That's a problem. There is another dimension that we regularly ignore in identification volumes that we can make use of in swath kind of volumes, and that is to say that we have the dimension of time. We have this same spectrum, or at least this same set of precursors, the same M over Z range of them at least, recaptured another 3.2 seconds later. So we could ask which ions arrive together and disappear together. This has been the keystone of how the folks over at Waters have dealt with MS to the E data volumes for forever. So they have a very long history in this, and there are in fact some open source tool sets out there for attempting to deconvolve these signals and to recognize these fragments from this swath belong together because they arrive at the same retention time and they fall away at the same retention time. And you can do the same in the low energy scans, the MS scans alongside that. So that same approach is still available to us here if we want to decide de novo, with no sense at all of what peptide sequences are present, which fragments belong together in a set. So that is an approach that is designed to make data-independent volumes, like those from swath, look more like data-dependent volumes. But I will note that data-dependent doesn't appear anywhere in my title. Instead, I've got IDA, and I'm gonna wake up Grant on this one. Why am I saying IDA rather than DDA? I'm thinking, I hope my information is still current, that data-dependent acquisition is actually a term that we carry over from the fine world of Thermo Fisher. And they didn't use the same name for doing data-dependent acquisition in TripleTOFs and in the preceding Q-trap instruments, because they use a method they call information-dependent acquisition. Am I correct on the naming of that? All right. So when we're talking about doing a shotgun discovery experiment, that's a little more generic, in the TripleTOF, we're talking about the use of its information-dependent acquisition mode. And the thing that I want you to think about as we do this is that even if you're doing an information-dependent acquisition experiment in a TripleTOF experiment, you should not assume that all these little steps that we take for granted are just the same in a TripleTOF as they are in a Q-Exactive. So I'm going to try to walk through some examples of where that comes into play. We're going to start with producing a quality MZML. When we produce an MZML tool, an MZML output from a raw file on a Thermo instrument, we're probably heading to some search engine that can't read raw files directly. Now, if you're using MaxQuant, you're probably just feeding it the raw file directly. But still, underneath the hood, at some point, the software must go through this process of turning peak profiles into sticks. So we're going to talk about how that problem spills out as we look at TripleTOF data sets as well. Now, I had 3 search engines that I really wanted to profile for this. MS-GF Plus is one that we've seen performs brilliantly, especially when we have low resolution fragments. Would it hold up well when we look at it in the QTOF context? Comet is an open source search engine by Jimmy Ng that has essentially identical scoring to the SCIEX algorithm. It's open source, it's fast, it has a lot of customizability, so I thought, let's try applying that in the context as well of QTOF data. And Andromeda, if you don't recognize the term, you may well have used it just the same, is the search engine built into MaxQuant. So I wanted to be able to show these 3 side by side on the same data set. And finally, we have this last little bit of information that we need to talk about, and that's to get from me to Bridget. I care a whole lot about the identification problem. Bridget is really helpful in dealing with all these quantitation problems. But at some point, we have to translate our information of what we've identified in the sample to what we're going to quantify in the sample. And that handoff is a little bit complex. So I'm going to try to talk about just some of the broad outlines of that. Now, I have a collaborator at CSIR in Pretoria, Stoyan Stoichev, who has produced some data sets for urine peptides. In this case, I've zoomed in on it using 2 different appraisals of the same thing. At the top, I have profile data. So I'm going to use my mouse as a laser pointer if I can make that work. Here we go. All right. So here we're looking at this narrow range, about 875 to 895. And here we have a series of fairly tall peaks. And I'm going to tell you that these are about 1/3 of an m/z apart from each other. Now, I could point to my grad student and say, why are they 1/3 of an m/z apart from each other? But I'm not going to put him on the spot today. But you in your mind should be thinking, these are 1/3 of an m/z apart because this is a triply charged precursor. So we have a peak, a peak, a peak, a peak, and that's all great. And we also have other ions in here. Some of them are not 0.3 m/z apart from each other. They're 0.5 apart from each other. Those are +2s. Now, what does it look like if you have a pair of +2s that are 0.25 m/z apart from each other? It looks like a +4, but we're not going to worry about that so much. This is one of the problems that we have to deal with when we're thinking about the intact peptide ion mass spectrometry. Now, I'm going to move ahead to zoom in a little bit. We're now looking at this +3, nice and close. Has anyone done this on a Q-Exactive raw file, looking at the MS scans? All right. So when you look at these peaks, do these look very skinny? Well, let's start with the first question. Are they baseline resolved? Can you see all the way down to the baseline to basically 0 intensity, separating those the intensities of different isotopes? I see someone shaking their head no. Are you seeing some scurf down here? There's a little bit of scurf. But mostly, this instrument is high enough in resolution to baseline resolve +3 and +4 ions, no problem. Now, if we get up to a +20 ion, are we going to be able to baseline resolve the isotopes? Maybe not. So this is an example of high resolution, time of flight mass spectrometry. In the old days, TOFs were not particularly good at this challenge, but the peaks have gotten a lot narrower. The ability to resolve peaks has gotten quite good, actually. So what we have then is the problem of how we go from this up at the top, this collection of intensities as a profile as a function of m/z, and turning that into a bunch of sticks, because that's what we're going to have when we deal with it in the identification problem. So we need to be able to produce this. Now these sticks down at the bottom were produced by a centroid algorithm that's built into the analyst software. And I know that because ProteoWizard, by default, the way everyone seems to use it, will call the peak picker that was provided by the people who sold us the instrument. So we have an agreement with SCIEX that allows us to ship their software library with ProteoWizard, and we can call that, we give it this profile mode spectrum, and it returns to us a peak list. Okay? So that's great. Now, the command line, I know I didn't show you a pretty GUI, I showed you a command line, but honestly, this is the same thing happening under the hood every time you hit the Go button on the MS-Convert GUI. This is a very standard tool, part of the ProteoWizard toolkit. So under the hood, we have a tool called MS-Convert. We're going to apply a filter on the data that we're receiving, and that filter is going to apply peak picking using just kind of the standard vendor library to all all MS scans and below. So MS, MS, however many levels of MS to the N you've done, all of them in this case will get turned into sticks from these waveforms. We try to use zipping in order to cause the files to become a little bit smaller, and in this case we can apply that very same command line to WIF files just as we would to raw files. So WIF and scan files, these are the things that come out of a TripleTOF experiment. So I've tried to unfold some of those down here. But I want to mention that there are a couple problems with that. First off, when we use the SCIEX libraries, we only have access to one peak picker. It is the one that the centroider that they built into their analyst software. Now, you might ask yourself, what kind of peak picking does SCIEX use when they send it to their very own search engine? They don't use the SCIEX, they don't use the analyst peak picker, Centroider. They use one that was created by the people who wrote the search engine. We don't have access to that. So we are not able to get the same peak lists to open source software that would be available to them by theirs. So we need to have something that can give us high performance on peak picking. The other thing that I find very difficult to deal with is that they never provided a library in this set of tools made available to ProteoWizard that lets us determine what is the precursor charge for each tandem mass spectrum. Isn't that odd? So let us look at what happens. Well, we'll get to that in one slide. I'm now giving you a much, much more complex command line for running MS-Convert, but it's the one that I'm going to be comparing everything to, so I want you to just sort of stay with me. We used Mexican hat wavelets. There's that term again. Right? So we have a wavelet matcher that attempts to find peaks out of these functions of intensity and M over Z. So that's, we were a little snarky when we wrote this software. We decided that we could no longer wait on high-quality peak pickers from some mass spec companies. SCIEX was not the problem here. They had provided us a peak picker, as I mentioned. But there was one company in particular that had failed to give us a peak picker for their data sets, and we could not wait anymore. So we created this tool called CantWait. We published it in 2015. You see right here, it's called the CWT peak picker, and it has a couple parameters I'm going to explain. That is SNR. SNR, that stands for Signal-to-Noise Ratio, which is to say that you can tell the software, I don't care about all this scurf down at the bottom. I want peaks that are big and I don't care about anything else. So if you set signal-to-noise ratio to 5, you're going to get a lot fewer peaks than if you set it to 1, like this. Next is peak spacing. Peak spacing. So you can tell the software that I don't want to see peaks created 0.01 mass units apart from each other. I want to see them at least 0.1 apart. More like the true resolution of the instrument. Now the other trick that we built in alongside CantWait is turbocharger. Turbocharger is able to look at the isolation window in the MS scan to say how far apart are the isotopes, and from that infer a precursor charge. All right. And again, we take some parameters. We can specify we only care about things ranging from charge of 1 up to charge of 4. We're still going to zip the file, and we're still going to apply this to all the whiffs. Okay, so do you need to understand what continuous wavelet transform looks like? No, we're not going to get into that. But we start from these Mexican hat wavelets, and we look for whether you need a big one or a small one, where it needs to be positioned, etc., in order to turn that into a set of wavelets, thus a set of peaks that can be matched to the spectrum. Okay, so when we look at exactly the same spectrum in the resulting MZML files, we suddenly see some differences. This selected ion section of the MZML file, who here has ever looked inside an MZML file? No. But some of you have generated them, I'm quite confident. All right, so when we look inside an MZML, we have a selected ion section that appears upstream of each MS-MS scan, and it provides information about the precursor. At the left, we have the one that runs, if you just run MS-Convert, like just as though you're dealing with the thermo raw file. Here we see that we have a selected ion mass to charge value of 448.86029, blah, 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 blah. And it even gives the type of unit. It is an M over Z. When I run turbocharger and CantWait on the software instead, I see that the ion M over Z has changed. It's no longer 448.8602. It's now 448.8627. So this is the first thing you got to think. The way that you choose what peaks represent your spectrum is going to cause variance in the recorded M over Z values for your observed peptides. So that's pretty important. The other thing that we get, though, is that we see the charge state is reported right here. That information is missing from all scans when we run ProteoWizard's MS-Convert in its ordinary mode on WIF files. So does that have any impact? Do we actually care? First off, I'm going to show that turbocharger is able to give us the charge state distribution when we run it. We don't have a huge number of scans here for which we have an unknown charge. We have these blue in these 3 replicates of urines that I've mentioned, that some number of +1s that make it into our data set. We have a fairly large number of +2s, a fairly large number of +3s, some number of charge 4s, but why don't I see any charge 5 or charge 6? I restricted them out. I forced the software to show me nothing bigger than +4. So we can see then that we're getting this distribution to work from. All right, now I mentioned the signal-to-noise ratio as an important parameter. If I run the standard peak lister that's built into Analyst, I see that I get, at the median, 179 peaks per tandem mass spectrum. If I use the CantWait at its default setting, 1.0, I see that I get only about 126. But in general, I felt that the numbers from the signal-to-noise 1.0 were similar enough to what we see from the vendor peak picker that I could still do successful identifications. As soon as I allowed that signal-to-noise ratio to increase, the number of peaks dropped way off, and I thought to myself, I don't want to do that to myself. I don't want to take away the signal that against which I'm trying to identify. So, does it matter whether or not you have precursor charge states? When I run Comet on MZMLs that are produced from ProteoWizard, using the vendor code or using CantWait and Turbocharger, I see that the number of PSMs that are generated is much, much greater in the vendor set. 181,000 versus 95,000. Why is that? Does anyone know what happens when you feed a tandem mass spectrum to a search engine and don't tell it what the charge state is? I'll tell you because this pattern was set way back in the mid-1990s, and I had a lot of conversations with the author, Jimmy Yang. What happens is that the software tries to determine, is this spectrum singly charged? But in doing so, it just asks, are all the fragments below the precursor M over Z? If it is, it treats it as a +1, and that's the end of the story. If it has fragments on either side of the precursor, though, it says, gosh, this thing is multiply charged. Maybe it's +2, maybe it's +3, I don't know. And so it'll try to identify it both ways. So you get two different assessments of what this spectrum represents. One under the +2 assumption, one under the +3 assumption. That takes time. So having precursor charges is valuable to you when you do your downstream analysis. It also takes a lot longer to run with Turbocharger and CantWait. Typically I would set up for my files to get converted to peak lists and then go home for the night. And when I came in the morning, they were done. But it's a lot slower than what you're accustomed to doing when you're doing MZML. So that's a big point in don't assume. Don't assume that translating these data to something you can use with your open source search engines is going to be easy or fast. All right, so did it matter in terms of the information yielded from those? This is Comet identically configured between these two. We see that the number of confident PSMs changed dramatically, 6302 versus 4601, and that the number of peptides that we had was also greater when we ran with CantWait and Turbocharger. So the way in which you produce your peak list will have a lot to do with your identification success downstream. All right. How do we run our search engines? I know people like graphical user interfaces. I really know. And I swear, I spent a lot of time trying to get comparable searches using a tool called Search GUI to run Comet and Andromeda and MS-GF side by side exactly the same way against each other. But I have to say, although the software appeared to be running the same search on all three search engines, it was not doing so. So, I'm not going to say more on that at the moment, but let's just say that I felt it necessary to run these search engines by the command line so I would know what was happening. So I have to give MS-GF Plus some memory to work with. Here I've given it 15 gigs of RAM. You don't have to give it that much, but I did. I had to tell it where to find its MZML files. I had to tell it where to find its PTM configuration. I had to give it a sequence database to work with. I had to specify a precursor mass tolerance. Now, this is where Grant stands up and starts shaking his fist. There it is. Thank you, sir. All right. So we have a problem here because when people sell you an instrument, they tell you the mass accuracy is good within small number, right? But as a bioinformatician, I'm trying to get not just like the good performing peptides, but all the peptides I can identify from that mixture. And while it's true that the dominant peptides in this mixture have less than 10 ppm mass error on them, there are a great many identifiable spectra that have much greater mass errors than that. So if I allow for a wide precursor mass tolerance, I identify more spectra from these files than if I allow for a very narrow one. So I'm not going to be running any 10 ppm search on these. I will not get all the information yield out of them. So I need to inform the software about my precursor mass measurements. I need to inform it about what kind of instrument collected the fragments. In this case, use the TOF analyzer mode. I need to specify that I'm going to control my false discovery rate by target decoy analysis. And I need to specify, because it's me, that I'm going to do a semi-triptych search, because I always do semi-triptych search. Anytime you have a few proteins that are highly abundant in the sample, you're going to need to do semi-triptych peptides to be able to identify much of the peptide coverage. Okay, so this is what the MS-GF search looks like. As you see at the bottom, I tried running this by Search GUI, but it failed to set the NTT and INST parameters correctly. When I told it that I was doing a TOF data set, it instead set up the MS-GF to run it as though it were a QExactive. That's not okay with me. All right. Comet params looks much like configuring sequest, if any of you have ever done that stuff, but I just want to note that I use the same peptide mass tolerance, nice and wide, 100 ppm. I'm allowing for some amount of isotope error, and I'm telling it that, like MS-GF, the software is going to subdivide the M over Z axis into bins, and if it has a peak in the bin where it's looking for a fragment, then it's going to say, okay, that's great, but if it falls outside that bin, too bad. So I need to set the bin size correctly. In both algorithms, I used about a 0.1 M over Z size bin for mass tolerance. Okay, so how did they do? First off, the number of proteins we get from biofluids is always poor, right? So don't hold this against the instrument, certainly. If you're running urine, if you're running serum, if you're running plasma, whatever into your instrument, the number of proteins you get is always going to be disappointing. So the number of peptides that we get and the number of spectra that we get is more relevant in this case. So we see that we had about 7,000 identifications by MS-GF+. We had about 6,000 by Comet. I want to say that when I did the Search GUI comparison for all three search engines against each other, I was told by the software that Andromeda had identified more spectra, that had identified 95% of all spectra that I had passed to it. Okay? So, not believable. That is not true. So I felt that these numbers, at least I understand where they come from, and I have some faith that these actually are real. So how do the search engines compare when we look at them? Now I'm going to contextualize this for just a moment. When I look at data from, that have been collected in an ion trap, like in an Orbitrap with high-resolution precursors but low-resolution fragments, I frequently see something like a 70% overlap between two different search engines that I've tried to configure just as similarly as possible. So how do we do? When I look at the number of spectra that have been identified successfully by both search engines, I see that there's about a 61.4% overlap on the median. When I look at the peptides, I see that there's a 63.7% overlap for the peptides. So here I'm splitting it out for each of the three replicates, and then on the left I have those that were identified by Comet only. At the right, I have those that were MS-GF only. In the middle, I have those that were found in common to both. What this suggests to me is a lesson that a lot of bioinformaticists over time have failed to recognize. And it's that I'm not that familiar with data of this type. I've spent a lot of time looking at ion trap data. I've spent a lot of time looking at HCD data in QExactives and Orbitrap, stuff like that. I have not spent as much time working in the world of TripleTOF. And so I don't know the optimal parameters. What if 60 ppm was the better setting for precursors? What if the fragment tolerance was way off? These things can make a really big impact in identification. And what I see in this case was that my identification overlap was lower than I really feel comfortable with. I'm in the 60s, and I'd rather be in the 80s or the 90s for this overlap. The mass accuracy that we have on these should produce a high degree of concordance among search engines. I was not able to achieve it, having spent a couple weeks trying to get to that place. So what is up with Andromeda? I mean, let's face it, I dislike max quant really significantly. But just for you, I spent a week, actually more like 2 weeks of my life trying to get Andromeda to give me usable search results. And I have to say that through your good offices, I have achieved one successful run in max quant, which was one more than I ever had in my life. So I'm pleased with that. However, I was not quite clever enough to figure out how to do single pass semi-triptych searching. I have an advisor I'm going to turn to on this one, and maybe we'll get that result included back in there. So running it through MaxQuant didn't work out quite the way I wanted it to. I felt that I couldn't understand what parameters I was feeding the software, and that made me pretty uncomfortable. So I thought to myself, well, I'll just use that handy-dandy tool SearchGUI to run Andromeda. And what I found was that Andromeda ran into some serious problems there. Remember that it claimed to identify 95% of all spectra I handed to it. That was a problem. And the reason was that SearchGUI was failing to communicate properly with Peptide Shaker about which hits were targets and which were decoys. Bit of a problem. So that wasn't great. I then tried running on command line Andromeda, just the one you can download separately. Command line Andromeda would not read my MZML files. So I threw it out. I threw it out again, and I'm sorry that I don't have a comparison to show you. I had to leave for vacation rather than spend another week on this. I'm sorry. So Andromeda is software that a lot of people use. It's obviously very significant. I was not able to get search results with it. How do we get from here? I'm sorry, I've really gone on way too long, haven't I? Feel free to hook me off the stage. You can. Oh, all right. So how do you get from IDs to a spectral library? The spectral library gives you the ability to determine where in a run a particular ID takes place once you do a swath experiment. So if you want to know where does this peptide appear, having a spectral library entry for that peptide allows you to look through the spectra for that swath very quickly and determine which one contains fragments of this peptide. Okay. Now, Skyline and OpenSwath are both good options for you, and it appears that there are very mature workflows already in place for connecting your IDs to the library search. So for the first of these, if you have PepXML files, which most search engines can write, if you have MZIdentML files, which many search engines can write, if you have an MS text file from MaxQuant, all of these can be used by Skyline by the good offices of BiblioSpec. BiblioSpec is the spectral library search engine made by the McCost Laboratory. It is able to take all three of these as inputs. So maybe you don't like Comet and you don't like MS-GF Plus and you really, really want to do your searching by MaxQuant. If so, you're okay. You can still pass that through to Skyline via BiblioSpec. So that's great. Now the transproteomic pipeline has very strong connection with OpenSwath as well. The transproteomic pipeline is not so very different really. It's going to use tools like peptide profit and protein profit to limit the false discovery rates. That can then be passed into OpenSwath. So if you enjoy that framework, you can certainly use it as well. So takeaways. ProteoWizard's default peak lister for the TripleTOF has some important gaps. If you are going to do free-form identification on information-dependent acquisition experiments with your TripleTOF, it behooves you to get your precursor charge states. And the way to do that is to run the triple charger thing. It does mean that it will take longer to generate your MZML files. So that is inconvenient. So budget some time for that. Expect to generate your MZMLs overnight rather than in the next few minutes. All right, it's an expensive algorithm. It is multi-threaded, so if you have a 12-core i9 processor, you're good to go. All right. Comparing Andromeda to other search engines on an equal footing, and I stress that on an equal footing is really the only way to do it, it continues to be a challenge. I can't create standard format exported IDs from the software, and that makes it rather difficult to compare head-to-head against these other engines. I'm still working on it. I'm still trying to meet you where you are on that score, but I'm picky and persnickety. So I hope sometime this year I will be able to get a semi-triptych single-pass search done in Andromeda that I can compare to these other engines. And with that, I'd be happy to take any questions. I know I've done a lot of detail.
David, thank you very much.
Sure.
Right, some questions for David about the complexities of data analysis.
They can be tough ones. Oh yes, Alex.
Thank you very much. So something that I'm still trying to just get clear in my own mind is that if I've done a swath experiment then, using our instrument, can I use that data in a discovery-like manner to just go and see what is different between the two samples?
Okay, that is a hard thing to do. generally speaking, a swath experiment is not the first one you want to do. You want an experiment in that class of sample to build your spectral library first, and then your life gets a lot better. Is it possible to identify peptides strictly from a swath data set? Yes. Is it effective? I don't know how to answer that question as well. As I've said in the prelude, one of the first things that people would try to do is to deconvolve which fragments belong to which precursors by arrival and departure times. RamClust, some software from Colorado State, is an open source approach to that. Of course, Waters has good software for that purpose, but you're not going to be running that against a SCIEX WIF file. So I think that this is an area that is less well known. Now, folks such as the McCost Lab have worked at doing this in situ peptide identification from data-independent volumes. They created an algorithm called Pecan. I don't know if it ever got published, but I think it got discussed at ASMS, and I think they've written a successor to that they think is much better. So being able to identify peptides in data-independent volumes will come along, but this is not where most people in proteome informatics have been working. There are a lot more people dogpiling into that space now, so I think that might get better. Yes, sir?
And if one had already a spectral library for all the proteins that you were interested in, then you could look at the abundances of these proteins?
Yes. Yes, absolutely. The trouble is that there's relatively small amounts of information-dependent acquisition sets for QTOF, for TripleTOF specifically. Not to delve into fragmentation chemistry a whole lot, but the way that we do CID in HCD and the way that we do CID in a TripleTOF are both beam-type CID. So I should expect that the fragmentation processes are similar. The detection efficiencies by M over Z are different, I should expect. So I don't know to what extent you can extrapolate from a QTOF, from an HCD spectrum and a Q exactive to a TripleTOF tandem mesh spectrum. I don't have experience there, and I'm not sure what the chemistry would look like. Good question.
So there's a chicken and egg problem here, isn't there, with spectral library deconvolution of data generation from instruments generating data on, in theory, every peptide, which has never been possible before. So by definition, we're generating a whole sort of spectra from peptides that nobody's ever seen before, but you need a spectral library to be able to interpret the data you've generated. Yeah. So doesn't that argue that we need to use the TripleTOF in the first instance as a bloody good data-dependent acquisition instrument?
They're pretty good.
To acquire more spectra, or to rely on community effort to build the peptide library slowly, sure, and hope that eventually we will have a library from every possible conceivable peptide. Or is it a solution?
Well, I've spent some time with identifications in the SCIEX world, right? So I've worked with data from their Q-trap, a Q1 like we have here, a collision cell followed by a trap. I've used data from those when I was working in federal trials for people trying to prove they had ricin in their refrigerators, right? You can do it. You can do identification with a Q-trap like that. I've worked with data from the Q-star XL and the Q-star Pulsar, is that right? Is that a model? And then I've worked with data, and then suddenly the Q-star Elite came on and I started paying attention. I was like, whoa, hey now, these are looking a lot better. And I have to say that when CPTAC did work with the TripleTOF, I became pretty impressed with what was achievable. For the first time, I really felt like there was parity between the best instruments from this world and from that world in producing ID. Now, once you get to maximum sensitivity, now you're looking at crap with a really awful signal-to-noise ratio. I don't understand all the things that go into the spectra that appear there. But I would say that if you just want to use this as a great shotgun instrument, you won't be disappointed. It's probably on the same level as like a Q exactive.
What about instead taking the other approach to build better algorithms to predict the theoretical spectrum for every single peptide?
I have been really surprised by the degree to which proteome informaticists are not interested in that problem. There are a few groups that have worked in predicting fragments from peptides, but it's a surprisingly small number, and I haven't seen people interested in that bent looking in the TripleTOF direction yet.
Because that seems the obvious solution to this problem, actually. If you can use robust and intensity predictors, not just fragmentation predictors, then you don't need to have observed the spectrum before. You can create your own in silico spectral library.
Yes.
For stuff you've never seen before.
Yes.
Because one of the questions in my mind here is whether with the TripleTOF, whether we will see more proteins or simply more peptides for the proteins we've already seen.
Well, I can already tell you the answer to that one. As a relatively cynical bioinformaticist, when you increase sensitivity by twofold, you double the number of peptides you see for serum albumin. Got you covered.
And that, yeah. And so that's my question really, is whether whether we do in practice see past that the limit of the more abundant proteins or not. I mean, in theory we should do, but whether we do remains to be seen.
Sure.
So.
But any time you have a new technique that doubles your identification sensitivity, whether it's on the instrument side or the informatics side, the gains primarily fall on proteins we've already seen.
Okay. Are there any other questions for David? I have one more, but I'll give everybody else a chance first.
Oh, Brandon's got one. Oh yeah, he's got a great question.
So my question was going back to actually was one of your slides here where you're talking about the mass tolerance that you were setting for your searches. And you said because you're in a position you want to get everything, not just the really good bits. But isn't there a potential problem with analysing high quality, low mass tolerance data with a wide mass tolerance? Aren't you going to increase your false hits in that data set?
Well, first off, 100
or
ppm.
your estimation of
100 ppm is not low resolution. That's still pretty good. I mean, that's like within 0.1 m/z. But yes, certainly the search could be different. So if I were to change these settings right here to 50 ppm, which conveniently I have done, the numbers of identifications are slightly lower.
Yeah.
Slightly lower.
So I'm wondering not so much about the number of identifications, I'm thinking about the false discovery issue.
I was controlling false discovery rate exactly the same way both times.
But isn't your true false discovery rate like to go up as you widen that mass tolerance window?
No. No, that's a misunderstanding actually. Just because you compare more sequences to a particular precursor doesn't mean target decoy falls apart. Target decoy falls apart if you force the precursor tolerance very narrow. So if I ran this to a 1 ppm search, then I could no longer trust my target decoy assessments. But increasing it to a broader one, that's not a problem actually.
That sounds counterintuitive to me. We need to talk about that over
Sure.
beer, I think.
Be glad to. My throat's parched, so I could use it.
Cool. Okay, are there other questions for David? Liam?
It's not something that you specifically dealt with in your talks, but it's something that came up in one of the other talks earlier where Rudy Ebersol provided that peptide map, and there's that beautiful spray across your retention time MFZ windows. My question there is as you get to higher MFZs, there are fewer and fewer peptides that come through. And so you are, if you have to look at a percentage of your dwell time that you are spending analyzing across there, how many of those give you high value information, so result in a good identification coming out of there? And how much of that is wasted time spent evaluating a space that potentially you could cut your dwell time down and get more cycles more quickly?
I believe that Nelson was showing 400 to 1100?
1200, I think.
400 to 1200, okay. So that's a range of 800 m/z. You divide that by 25 m/z to get the number of swaths that you'd have to cut across that. So let's say that you change from 25 m/z swaths to 12.5 m/z swaths, right? So now each swath has less crosstalk, so the fragments have come from half as many peptides. So our identifiability goes up, but the time with which we sample each chromatogram halves. So that's not good. So yeah, there's always this push. You want to keep the range of m/z's you're considering overall to be the sweet spot, where all your +2s and +3s are probably. So, I mean, you're not going to be looking for +1s. So there's not a whole lot of value in jumping out to 2,000. But yeah, you've got this multi-parameter fitting problem. You want to be able to sample each chromatogram as frequently as you can, but you want to be able to discern the fragments of one peptide from one that's completely at a different M/Z as well. So yeah, that fitting problem continues to be a big issue.
Right, David, thank you very much.
Yeah, thanks.